if anybody misses it, again, you can always look at it. I don't find that too many people are looking at them, but every so often I do notice that somebody has taken the opportunity. Again, it's not only if you've missed a session, but if you want to review something. Okay. All right, Kaimani, I actually saw you came on very early, and when I take attendance, I'll keep in mind that you're here. Okay, so let's do this example. And again, you don't have to talk to me. I mean, I'd like if you talk to me. I'm glad when people speak up. It gives me some incentive to that I see that there's somebody there. But again, you can always send me a chat if you don't have, if your mic doesn't work. I know that everybody has a mic on their whatever computer or tablet or whatever they're using. Usually tablets are not a bad thing to use for this course because it's not so small, and also you have the mic and the video. But let's go on with this problem. We're asked, and this is a very typical question of something that could happen, a real life situation. This is what we call a mathematical model, a real life situation. Suppose you took out a student loan for $2,300. That's not a lot of money. Sometimes you take out loans for a lot more. Now, the interest rate that you got is 7%, and it's compounded monthly. Now, when you take out a student loan, usually they give you the option of not having to start to pay back that loan until you graduate. So let's say it takes you 6 years to graduate. And now you want to start paying back the loan, and you want to know how much you owe at this point. So it's compound interest. If you remember, this is the formula for the compound interest. If you're getting a question on compound interest, they will give you the formula. They will not ask you to figure out the formula, but you're going to need two things. Number one, you need to know what each of the letters stand for, obviously, and you have to know how to put it into your calculator, because the only way these problems can be done is really with a calculator. Now, A is the amount of money we're going to be looking for. The P is what we call the principal. The principal is the original amount of money that you borrow, or the money you put in the bank, if this is money you're putting in the bank, and that's $2,300. The next letter we see is R. R is the rate of interest, but it has to be written as a decimal. So if we take the rate of interest, which is 7%, and convert it to a decimal, remember it means move your decimal place 2 places to the left. It's going to be 0.07. A common error on this is somebody might put just 0.7. That would mean you have a 70% interest rate, which is, I don't know, would be outrageous. Okay, the T is the total number of years you're borrowing the money for. And in this case, we were told that it's 6 years. And the N stands for the number of times each year the interest is being figured out. It's the number, it's called the number of times the interest is compounded. Now, the hint is that they told me that the money was going to be compounded monthly. And when you compound something monthly, how many times a year are you doing that? Obviously, there are 12 months, so your N is 12. So now we have all the numbers that we need to stick into our calculator. We're going to do A equals, and I'm going to put it down the way you should be putting it into your calculator, 2,300, that's your P, Open your parentheses. You should have a parentheses button on your calculator. You don't have to be using one of these. As a matter of fact, you shouldn't be using one of these graphing calculators. You should be using a regular scientific calculator. It does have a parentheses button. Then you put the number 1, the plus button. The R we know is 0.07, so you put in 0.07. You divide that by n, and we know is 12. You close your parentheses, and then you have to do n, which is 12, times t, which is 6. Now, the 12 times 6, I think you should figure out first before you put it into your parentheses. Now, we know what 12 times 6 is. It's 72. That's why you cannot do this in your head. You must have a calculator because you're doing something to the 72nd power. You're using an exponent of 72. Okay, I'm putting this into my calculator. 2300 parentheses 1 plus 0.07 divided by 12, close my parentheses, press my exponent button. Remember, the exponent button usually looks like this, and you put in 72. And then you press your equal or enter button. And what I got as an answer is 3496.242. Now you're only going to go to 2 decimal places because this is money. So this is dollars and cents. Since the number after the 4 is another 2, we don't raise this, we leave it at the 4. So at the end of your 6 years of school, you will now owe $3,496.24. Even though you just borrowed $2,300, the rest is interest, and you've got to pay this whole full amount back. Okay, and we said that this was what we call an example of an exponential equation or an exponential function because one of the variables that we're using actually is in the exponent. Okay. The 12 comes from the fact that the interest rate is 7% compounded monthly. The word compounded tells us how often during the year they are figuring out the interest. That is what the N stands for. The number of times the interest is figured out in one single year. And as I said, that term is called compounded. Now, when it says it's compounded monthly, it means it's doing it once a month, which means in a whole year, it's doing 12. So that's where the 12 comes from. If it would have said compounded quarterly, which is another common way, quarterly means every 3 months, actually, which means it's 4 times a year, and then your N would be 4. Does that make sense now? Okay. All right, so let's go on from here. Let's go on to the next section on this chapter, which is something called logarithms. probably one of the simplest type of exponential functions is something that looks like this. Y equals 2 to the x. Let me just reiterate what we had said the last time. 2 is the base. That's a number that has the exponent. It must be a positive number. X is one of our variables. Y is our other variable. If I were to make a chart of values for X and Y, for example, I could pick X to be equal to 1. And then my Y would be 2 to the 1, which would be 2. If I pick X to be 2, then Y be 2 to the 2, which is 4. I'll do a couple of them more. If X is 3, then my Y is 2 to the 3rd, which is 2 times 2 times 2, or 8. Notice these numbers of the Y's keep doubling because this is what's called exponential growth, or exponential, something increasing at an exponential rate. Let's see what happens if I use 0. Well, in that case, Y would be 2 to the 0, and anything to the 0 power is 1. And what if X would be negative 1? Then Y would be 2 to the negative 1. Remember what a negative exponent tells us. It tells us to take its reciprocal. So that would be 1 over 2 to the 1, which is a half. Let's do one more. What if I picked X to be negative 2? Then my Y would be 2 to the negative 2, which is 1 over 2 squared, or 1/4. Notice all my answers for Y are always positive. Sometimes they're getting bigger, sometimes they're getting smaller, but they never are negative. The answer, Y can't be negative, because any number to a positive number to an exponent will always give you a positive answer. This is also sometimes called f of x. We could call it f of x, or we could call it y. But this is an example of what we call an exponential function. The variable is in the exponent. We know what the base is. We don't know what the exponent is. We're taking different values for exponent. Now, the way I set it up, where I had y equals 2 to the x, or f of x equals 2 to the x, I was giving you different values for x, and you were giving me the values for y. Now, every so often, we don't want to concentrate on the exponent. We want to concentrate on the y value. What if I were to tell you what the y is? What if I told you I have y is 8, and I want to find out what x is? Now, this is a little bit awkward, but this is what's called the inverse. We're doing the opposite. Usually we start with the x and we look for the y. In the inverse, in the opposite operation, we start with the y value, which is basically the answer, and we're looking for the x. Now, I know how to put, if I'm looking for this, like if I'm doing 2 to the 3, I know how to do that. I can either do it in my head or I can put it in my calculator. But if I'm doing something like this, where I'm giving you the answer and I'm looking for the x, that's something you either have to know on your own. It's not something you could directly set into your calculator. And obviously, what we're doing is we're concentrating on something else. So very often what we do is we use a different method of setting this up. We're going to be saying the same exact information, only we're going to use a different way of, a different type of terminology. And that type of terminology is something called a logarithm. I'm not sure if I spelled it right. Well, it'll have to do. What does a logarithm mean? I'm sure you might have seen in some point something that looks like this. Log 2 8 equals 3. You may have seen that written, but what does that mean? Well, let me give you the interpretation. It actually means the same thing as 2 to the third power equals 8. These two statements are exactly the same. This is the exponential format. This is the logarithmic format. In general, if I write something like log base b of a equals c, and notice what I'm writing. I'm writing the word, the three letters log, which stands for logarithm, with a subscript b, with a letter next to it. In other words, this is on the same level. This is a subscript equaling c. What that means is that if we take the base b, the number b, and put it to the exponent c, that is going to give us the value a. These two things are identical, and they, as I said, they mean the same thing. They're just looking at things from a different perspective. In this perspective, usually what we're given is the base and the exponent, and we try to figure out the number a. That's what we were doing over here. I gave you the base. We knew the base over here was 2. And I gave you the exponent. Those were our x's, and I found the value a. When we do the log form of it, it's when we still have the base, but what we have is the final answer, and what we're looking for is the c, which is the exponent. If you use the word exponent instead of the word logarithm, it might make more sense to you. Log, meaning exponent, that you put on base b to get a is c. Now, one of the first things that you have to do is be able to change from logarithmic form to exponential form, or from exponential form to logarithmic form. Now, usually the most what we do is we change from logarithmic form to exponential form because we're more familiar with exponential form than we are with logarithmic form. So I might give you something that looks like this. Log base 10 of 1,000 equals 3. Listen to how I read it. The log with base 10 of the number 1,000 is or equals 3. I will do this one, then I'll give you a few to try. Remember, to change this to exponential form, I take my base, which is always at subscript, so that's the 10, put it to the exponent. Now the log equals the exponent. Log is the exponent. Exponent equals 3. So it's 10 to the third exponent will equal this number over here. That's next to the word log. And obviously this thing makes sense. 10 to the third does equal 1,000. And it looks much more familiar than it does in this format. But again, it's telling you the exact same thing. Okay, let's try a couple of these. I'm going to give you a couple to convert, and then I'm going to give you a couple that, let me show you how we could possibly have an equation with a logarithm and how we would solve it. So let's do one of those first, and then I'll give you some to try on your own. So let's say it gave you this question. Log base 2 of x equals 4. Now, again, it's hard for me to answer an equation that looks like this because it's not so familiar. So usually, a lot of the questions that you'll be given on logs will be able to be answered just by switching from their log format to the exponential. So let's change this to the exponential format. Remember, the subscript is the number that's going to have the base. So 2 is going to be our base. The exponent is always the number on the other side of the equal sign, the thing that the log, which remember log means exponent, the log is equal to. In this case, the exponent is 4. That always equals the number that's next to the word log, which in this case we don't know, it's x. But now this becomes a much easier example to solve because it's an exponential form, which is much more familiar to me. I want to do 2 to the 4, which means 2 times 2 times 2 times 2, which gives me 2, 4, 8, 16. So I get x equal to 16. So that's how, by converting something from log format to exponential format, we're able to solve a lot of the questions. Let's see if we can do some examples. Okay, I'm going to give you, first of all, I'm going to give you 3 or 4 examples to try, then I'm going to, while you're doing them, I will take attendance. Okay, first of all, here is something written in exponential form. 5 to the negative 2 equals 1 over 25. This is a true statement because we know a negative exponent means take a reciprocal, and so we're doing the reciprocal of 1 over 5 squared, so which is 1 over 25. I want you to write that in logarithmic form. Okay, so this one is going to be written in logarithmic form. Change that to exponential form. Okay, and now here are 2 equations that I'd like you to solve. So let's see if you can do all 4 of these problems while I take attendance. Okay. So the first 2, we just want to change their format. The first one is written in an exponential format. So we want to change that to logarithmic format. Okay, remember the basic thing is we have a log with a subscript, a number over here, the three numbers, an equal sign, and a number on the other side. The subscript is always the number that is the base. In this case, our base is 5. The number on the other side of the equal sign is always the exponent. So this is 5 to the exponent -2. My log, or my exponent, is -2. And the number that goes next to the word log is the final answer that we would get. If I put 5 to the -2, it'll give me 1/25. So you should have had something that looks like this. Okay, let's look at number 2. Number 2 is in the log format, and we want to change it to the exponential format. So again, the subscript is the base, the number that's going to have the exponent. The number on the other side of the equal sign from the word log. Log is another word for exponent. Log equals exponent equals. The exponent in this case is 4. That equals the third number, the 81. And of course, that is also a true statement because 3 times 3 times 3 times 3 will give you 81. Okay, the third one says we have the log base 2 of 128 equals x. We're going to write this now. And again, most law questions are almost completely solvable by changing them to their more familiar format of the exponential. So my base here would be 2. My exponent is this x, the number on the other side, and that's going to give me 128. Notice, what am I asking you? I'm trying to find out what exponent should I put on 2 to get me to 128. So I'm going to do this with my hands or with my calculator. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2, we're up to number 6, is 64. And 64 times 2 is 128. I got to 128 by multiplying the 2 7 times. So it must be that my x is equal to 7. My exponent that I would put on 2 to get the number 128 is 7. And the answer, let's do number 4. We have log base 3 of x equals -2. So again, switching this to exponential form, my base is still going to be the subscript 3. The exponent is now going to be -2, and that's going to give me this x. Now, what happens when I do 3 to the -2? Well, that means I have to do the reciprocal. I have to put 1/3 and make the exponent positive, which gives me 1/3 squared, which is 1/9. So the answer to number 4 is 1/9. And notice the answer, notice sometimes the x is on the other side. Doesn't matter. Any one of these 3 numbers could be your x, as long as you switch it from the log form to the exponential form. You're going to be able to solve the question. Does anybody have any questions about this at this point? Okay, so let's go to the next step. We're going to talk about now the properties or the features that are important for logs. And as long as we keep in mind that the log means the exponent, and the properties of logs are really the properties of exponents. So I'm going to demonstrate four important properties that logs have. And I'm going to do it, but I'm going to use a simple base. And you know what? The base I think I'm going to use is 10. And the reason I'm going to use base 10 is because it's very easy to do. 10 to the squared is 1,000. It's really easy to keep track of the exponents when you're doing things with base 10. So let's say I'm going to take two numbers. Let me take my first number A to be the log base 10 of 1,000. And let my B be the log base 10 of 100. I wrote base 2, but I really mean base 10. Okay, so I have these two numbers. I want to know if we can figure out what these numbers are. Wait, let's start over again. Let me do it a simpler way. Sorry, starting something. Let's take A to be the number 1,000. And let's take B to be the number 100. Much easier that way. Okay. Now, here's what we want to do. What do you think the log of A in base 10 is going to be? This is a very often an important question that we're asked. What is the log of a number? I know the base of the log. I know the number. What is the log of that number? Now, there are two ways of figuring this out. One way is to just do it the way we did before. I don't know what it is, so let's call it X. And of course, then I'm really doing the log of 1,000 at base 10, which we're calling X. And 10 to the X is 1,000. 10 to what exponent should I put to get the number 1,000? And I think everybody would agree that X would have to be 3. In other words, if A is 1,000, the log base 10 of A has to be equal to 3, because 10 to the 3 will give us 1,000. Let's make a comment about log base 10. Actually, I must put down what the base is that I'm using when I'm doing logs. There's one exception, and that's when you write just plain log. If I were to write log 1,000, and I don't put any subscript there, it's not that I forgot the subscript. It means that it's talking about a specific type of log. It's talking where the base of the log is understood to be 10. It's called the common log. In the common logarithm, the base is equal to 10. So anytime you see the word log written and no base is written next to it, you understand that that base is 10. So this is asking you, what is the exponent that I should put to base 10? Remember, it's not written in, so it's understood to be 10 to get 1,000. And of course, we know that answer is 3. So if ever I write a log and I don't put in the base, you will understood that the base I'm using is 10. I'm using a log base, a common log. And by the way, if you look on your calculator, you probably will discover a button that says LOG on it. It might look like an L, it might look like an I, it might be lowercase. That button specifically is a log button that we're talking about, and it actually means the base is 10. So if I ever want to find the log of a number whose base is 10, I could just press that button log, put in the number that I want, which in this case is 1,000. And when I press enter, I'll get that 3, because what the calculator is giving me is a log whose base is 10. Okay, so I'm going to go over here and just write log 3. Whenever I write log, it's going to mean that my base is 10, and therefore I know that the log of A is 3. Okay, let's go. Let's go back to our A's and B's now. What if I ask you, what is the log of B? Now, over here, I know B is 100. So I'm asking you, what is the log of 100? And again, I didn't write in the base, so we understood the base to be 10. So what number would that be? 10 to what exponent will give us 100? And I think everybody will agree it's equal to 2. And you could check that on your calculator by pressing your log button and putting in 100, and you will see that the answer you get is 2, because 10 to the 2 power will give you 100. Okay, now I'm going to do a few things with these numbers A and B. The first thing I want to do is multiply A times B. Obviously, when I multiply A times B, I'm going to get 1,000 times 100, which is going to be 100,000. So I want to ask you, what is the log of A times B? Let's just write it AB. Again, we're doing everything base 10, which means I'm asking you, what's the log of 100,000? How many times must I multiply 10? What exponent should I put to 10 in order to get to 100,000? And I think you might realize from, didn't learn this in college, you probably learned this in elementary school, that all you have to do is count the zeros. There are 5 zeros here, so that means it's 10 to the 5th power. So obviously the log is equal to 5. Because the log is the exponent that I would put to 10 to get 5, to get 100,000, and that's 10 to the 5th. Now I want you to look at something. What did we do to the log of A and the log of B in order to get the log of A times B? Normally, you would think I have A times B, I should multiply the 2 logs. If I'm multiplying A times B, well, multiply their logs. That sort of makes sense. But we see we didn't multiply their logs. We actually added them. We multiplied the numbers. We multiplied the 1,000 times 100. But when it came to the logs, instead of multiplying the numbers, we were adding them. But if we think about logs being exponents, then the thing will make sense. Because when you multiply numbers, what you do is you add their exponents, and the logs are exponents. So my first property or my first rule of logarithmetic is that the log base b of a times b, notice I'm putting in a base and I'm using a small b. It could be any base because this doesn't work just for base 10, but for any base. It's equal to log of a plus the log of b. When we're multiplying numbers, we add their logs. Okay? And it makes sense because what we're doing is working with exponents. When we're working with logs, we have to work with exponents. Notice the rules for logarithmetic are really different from the rules of regular arithmetic because we're working with exponents. Okay, now what if I did a divided by b? In that case, I would be doing 1,000 divided by 100. And I know when I divide 1,000 by 100, my answer is 10, which is 10 to the 1. Just putting in the exponent. So now let's look at it from log point of view. What should I do to the log of a divided by b? What should I do to the logs? My log of a is 3. My log of b is 2. What is a log, by the way, what is a log of a over b? What is a log of 10? Remember that log is the exponent. The log of 1,000 divided by 100 is the log of 10, which is simply 1. And if you think about it, it must mean that what I've done is I subtracted the two exponents. And that makes sense because really a is 10 to the third and b is 10 squared. And when I divide numbers, what I do is I subtract their exponents. That's why I got 10 to the 1. So the log, the exponent is 1. So my second property of logs or rules for log arithmetic happens to be when you divide. If you have log of a divided by b, you don't divide the exponents, you don't divide the logs. What you do is you subtract. It's the log of a minus the log of b. Because again, when you're dividing, what you do to the exponents, which are your logs, is you subtract them. Okay. All right, let's go a little further. I need some more board space. Let's say I take the number 100 and I raise it to the 4th power. Now, of course, you can do this on your calculator. You could do 100 divided by the 4th power, which is 100 times 100 times 100 times 100, which gives you a 1 with 1, 2, 3, 4, 5, 6, 7, 8. I did something wrong. Which gives me 100 million. Just checking this up on my calculator, making sure I did this correctly. One, two, three, four, right. It's 100 million, which we could write how do we write 100 million as in terms of 10? Isn't that 10 to the 8th power? And that really makes sense. Why? Because 100 is really 10 squared. And 10 squared to the 4th power, remember when we have something with an exponent raised to second exponent, what we're doing is we're multiplying exponents. That gives me 10 to the 8th. So how does this affect logs? Suppose I want the log of 100 to the 4th power. Well, I know what that answer is going to be. The log has to be the exponent. That has to be equal to 8. How do we get it? We took the log of 100, which we know is equal to 2, and we multiplied it by, we took the 4 over here and multiplied it. We take the exponent, the new exponent, and multiply it by the log. Why? Because the log itself is an exponent, and when you have something that originally has an exponent and you raise it to a second exponent, what you're doing to those two exponents is you are multiplying. In other words, if I want a rule for this, the log of some number to the nth power, if you're raising your number to some exponent, when it comes to the log, you take that exponent and you multiply by it. The exponent becomes the coefficient. You move this to in front. In other words, if I had something like log base 7 of x to the 4th power, doesn't matter what these numbers are, I see an exponent, that exponent becomes the coefficient. It becomes 4 log base 7 of x. Because when you're raising the log base 7 of x is the exponent, you're raising it to a second exponent, which means you're just multiplying those two exponents. So that's rule number 3. And I told you there are 4 rules. Let me give you the 4th rule. The 4th rule is really just an offshoot of rule number 3. Suppose I had the number 100, and I wanted to take the square root of 100. Well, if you remember, another way of writing square root is to use an exponent. This is the same as saying 100 to the 1/2 power. Fractional exponents are the same thing as roots. The square root is the 1/2 power. The cube root is the same as the 1/3 power. The 5th root is the same as the 1/5 power. So I can do roots by just writing them as exponents. They are fractional exponents. When you're working with this chapter on logs, we never do square roots or cube roots. We only do exponents. So if I have to do something that involves a root, I right away convert it to an exponent and then use the exponent rule, which means, suppose I asked you to do, this is, I'll call it rule 4, but it's really part of rule 3. If I want to do the log of the, let's call it the nth root of a, then what I'm going to do is actually do the log of a to the 1 over n, which means I'll multiply the log of a by 1 over n. In other words, when I'm doing the square root, I'm going to multiply the log by 1/2. If I'm doing the third root, I'll multiply the log by 1/3. And these are my 4 rules of, I'll call them logarithmetics. These are what we call the properties of the log. And now I'm going to show you, demonstrate how we can use these rules. Okay, I hope you have these rules written down because I have to erase them. You should have the rules in front of you. Okay, here's the instructions. They're asking us to, this is called write in expanded form. What we want to do is tell, this is a 6. My base here is 6. We want to know what to do to the individual logs to get the log of x squared times y fourth. So I have to think what operations are going on here and convert what I do in regular arithmetic to logarithmetic. What do I mean by that? It means if I see some things are multiplied, I know in logs, I'm going to have to add them. If I see things divided, I'm going to have to divide. If I see their exponents, I'm going to make those exponents the coefficients. So my step 1 is to look for anything that involves multiplication or division. In my example, x squared y fourth, I do see some multiplication. I don't see any division. So we have multiplication as, again, that's the first thing I look for. When it comes to logs, I know the rule is when I'm multiplying the numbers, what I must do is add the exponents. I must add the logs. So this becomes log base 6 of x squared plus log base 6 of y to the 4th. The logs, remember, are these exponents. If I take the exponent of the x squared and the exponent of the y squared in base 6, I'd have to add them in order to, because I'm multiplying the numbers. Notice I'm putting the word log in front of each, because I'm telling you, this is what I'm doing to their logs. This is what I'm doing to their exponents. Okay, remember, multiplication will change to addition. Division will change to subtraction. There's no, if the things are added already, then you can't simplify them. You can only simplify things that are either multiplied, divided, or if they're exponents. So the next thing I look for is exponent or radical. If it's a radical, you change that to an exponent. I don't have any radicals here, but I do have exponents. When I have an exponent, what I do is I take that exponent and I make it into the coefficient. So here the 2 is going to be the coefficient. It's going to be what we're multiplying the log of x by. And this has an exponent of 4, so that's going to become the coefficient over here. So in my final result, my answer will be 2 log base 6 of x plus 4 log base 6 of y. I have expanded from the one single log into a couple of logs, but all I'm doing is I'm just doing the log of x and the log of y. I've expanded it into the individual logs. Let's try another one. I'm going to do one more, and then I'm going to give you one to try. Again, you're going to have to be looking at your rules for logarithmetic in order to do this. Log of square root of x, y, the y is outside the exponent, over z to the third. I'm putting a line through it so it shouldn't look like a T or a number 2. Okay, notice I did not put any base here, but we know that's not a mistake. It means that my base here is 10. It's a common log, and therefore I don't have to write the number 10 in. But what I do see is I want to make sure, first of all, that since I see a radical in it, I'm going to rewrite this as something with an exponent. The square root of x is equal to x to the 1/2. Remember, the regular square root is a 1/2 exponent. So this is x to the 1/2 y divided by z to the third. So that's the first thing, is actually that should be my first thing. If you see any radicals, change them to exponents. Now, we look for anything that involves multiplication and division. And I see the x to the 1/2 is being multiplied by the y. So in terms of logs, we're going to have to add them. So it'll be log of x to the 1/2 plus log of y. And since I'm dividing it by the z to the 3, I'm going to have to subtract the log of z to the 3. So I took care of the multiplication and division by changing anything that was multiplied to adding, anything that was divided or in the denominator gets subtracted. If there were several things in the denominator, I'd have to subtract all of them because they're all in the denominator, which means they all have to be subtracted. Now I go back and look at the exponents and make those exponents into the coefficients. So this will become 1/2 log x plus log y minus, now there was no exponent there, but here there's an exponent of 3, so that comes in front, 3 log z. And that's my answer in expanded format. Okay, let's see if I can give you one to try. See if you can expand this. I'll give you a couple of minutes to try this out. Work on this together now. Notice I'm not using log base 10. I'm using log base 2. I see the base is written in. But the rule is the same. First of all, I look for anything that has a radical in it. There is a radical here. I'm going to rewrite this. I'm going to write this as log base 2 of 8. Instead of writing the square root of x, I'm going to write x to the 1/2 power over y z squared. So that's my first step. I never work with radicals in log equations or in anything that has to do with logs. If I see a radical, I right away write it in exponential form as an exponent or fractional exponent. And now I remember my step 1 is to look for anything that involves either multiplication or division, noting that anything that's in the numerator, that anything that's being multiplied is going to be added. Anything that's divided is going to be subtracted. So I'm going to do the log base 2 of 8 plus the log base 2 of x to the 1/2 minus, now here I'm going to have to be subtracting, I'm going to put a parentheses because I'm subtracting anything that's in the denominator. Why? Because anything that's in the denominator is actually being subtracted. So it's going to be the log base 2 of the y plus the log base 2 of the z, squared, I'm sorry. Have to include all the exponents. Notice I had to put this in parentheses because not only was the y in the denominator, also the z squared. And if I would have not put in this parentheses and I would have just put in plus, it would have looked like I'm multiplying the whole thing by z squared. But I'm not. I'm really dividing by the z squared because it's in the denominator. Now I go back and I change and take anything that's an exponent, and there's one here, and there's one here, and put it in front of the word log. It becomes the coefficient of the word log. The exponent becomes the coefficient. So this becomes log base 2 of 8 plus 1/2 log base 2 of x minus parentheses log base 2 of y plus 2 log base 2 of z. There are two other things that I could possibly do with this. Number one, I look at this thing that says, just bringing this over here. We have over there log base 2 of 8. What does log base 2 of 8 mean? Let's call it A. What does that mean? Well, I know if they ask me what the log base 2 of 8 is, I would have to switch this from the logarithmic form to the exponential form, which would give me my base, which is 2. My exponent is the small a that I'm calling it, and that has to be equal to 8. So I think 2 to what exponent will give me 8? And that happens to be something I do know. 2 to the 8 is 2 to the 3 will give me 8. So the a would have to be the exponent 3, because 2 times 2 times 2 is what gives me 8. So I can simplify this thing by saying log base 2 of 8. That could have been simplified just to the number 3. Remember, that's what my a is, the log base 2 of 3. So this becomes just the plain number 3 plus 1/2 log base 2 of x. And if I wanted to, I could leave this in parentheses, or I could remove the parentheses by thinking of this as a -1 and distributing the negative and saying minus log base 2 of y minus 2 log base 2 of z. Again, it could be left in the parentheses, or the negative can be distributed. But don't forget, this 2 log base 2 of z is also in the denominator, so it also had to be part of what we were subtracting. So that's what we call expanding something in terms of logs. We could also be asked to take this and go back and take it from the expanded version and contract it back to a single log. We'll do that next time. What I want to do is show you a really practical type of use of this log that we can use using our calculators. And again, this is something you're going to have to use your calculator for. Make sure you have your calculator and know how to use it. One of the things that we like to be able to do is to solve what's called an exponential equation. Here's an example of an exponential equation. Suppose I tell you I have 3 to the x plus 1 equals 27. It's called an exponential equation because what we're looking for, our variable, is in the exponent. One way of solving an exponential equation is to try to put both sides in terms of the same exponent. Write them both in terms of the same base. This is written in base 3 because it says 3 to the x plus 1. Try and write 27 in base 3. Well, we can do that. 3 times 3 times 3 is 27. So I could convert the 27 to the 3 to the third. Once I've done that, once I have both sides written in terms of the same base, I don't have to worry about the base anymore. All I have to worry about are the exponents. And these two exponents have to turn out to be the same number. So that must mean that the x plus 1 has to equal this 3. And we get a very simple equation. And that gives me x equals 2. What if I gave you this? Here's another equation. I'll give you a couple minutes to think about it. 5 to the x equals 1 over 125. Think about what you would do with that. How could you solve that equation? What should we do? We're here obviously using 5 as our base. What should I do with the 1 over 125? Well, let's first think about the 125. Can I write 125 in terms of base 5? Let's try it. 5 times 5. All I have to do is keep multiplying the 5s until I get to 125. 5 times 5 is 25. And 25 times 5 gives me 125. So this must mean that the 125 can be written as 5 to the 3rd power. Now this is just plain, and this is in the denominator. But I know 1 over 5 to the 3rd power is the same as 5 to the -3. The way it became a fraction, the way it became a reciprocal is because its original exponent must have been negative. So 1 over 5 to the 3rd can be also written as 5 to the -3, which means that my x is equal to -3. So the fact that it was in the denominator told me that I'm going to have a negative answer, because the only way I could get a negative answer, get a fraction, would be if I had a negative exponent. Okay, I want to show you a different way of doing these. Also a way that will solve some equations that you couldn't do before. Suppose I asked you this question. 3 to the x power is equal to 17. 3 to the x power equals 17. I know 3 times 3 is 9, and 9 times 3 is 27. I skipped right over 17. I got to 9 with exponent of 2, and then my next exponent was 3, and that gave me 27. And that's very likely that's something that could happen anytime. Who says that the number over here that they're giving you can be written in the base that they're giving you? How do I know I can write 17 in base 3? There's a way of using logs that can solve this question. It actually is an example that we do by using our log button on our calculator. And remember what the log button on our calculator is. It's a common log, it's a base 10. So what I'm going to do is, since 3 to the x equals 17, I'm going to take the log of both sides. I'm going to write the word log in front of both sides of this equation. I will get log of 3 to the x is equal to the log of 17. You may ask me, why am I doing that? Obviously, because I have an ulterior motive. But I don't think you'd say I can't do it. If the two numbers were originally the same number, if 3 to the x equals 17, then the logs of their numbers must be the same as well. Well, the reason I'm doing it is because I know when I'm working with logs, exponents become coefficients. So I could rewrite this statement, log of 3 to the x, as x times log 3 equals log 17. And then, since I want to get the x alone, I'm going to isolate the x by dividing out the log 3. X is being multiplied by log 3. I want x alone, divide by log 3. Now, this is something I have to stick into my calculator. It's not something that I can do without a calculator, but that's what I do. On my calculator, I press my log button, I put in 17. It'll probably open a parentheses, so I'll close the parentheses. Make sure you close the parentheses. Divide, because it says over. Then press my log button again, and it'll open up a parentheses, so I'll put in 3 and close my parentheses and press equal. So log x 17, divide by log 3 equals, and I get the answer 2 point, now it's a long decimal, I'm going to go to 2 decimal places. 2.578 is rounds off to 2.58. The exponent that I should put to 3 to get 17 is 2.58. And you could even check this on your calculator by doing 3 to exponent 2.58. It won't come out to exactly 17 because I rounded this, but it'll be very close to 17. We knew it had to be someplace between 2 and 3 because 3 to the 2 was 9 and 3 to the 3 was 27 and 17 is in the middle there. So we knew that that does make sense that the answer. So I am able to solve what's called an exponential equation where I'm looking for the variable by using logs, and I'm actually using common logs. Just as an aside, suppose you found this question really hard. Suppose you found that question 5 to the x. Let me erase this. Go over here. Equals 1 over 125. A very hard question because of that fraction. You could do it the same way we did over here. Write the word log in front of both of these expressions. The log of x to the of 5 to the x is the log of 1 over 125. And remember that the exponent then becomes the coefficient. So this becomes x log 5 equals log 1 over 125. And then divide both sides by log of 5. And that's exactly what I'm going to do. In my calculator, I'm going to press my log button. I'm going to put in my parentheses 1 divided by 125, because that's what this is. And then I'm going to divide this by the log of 5. And let's see if we don't get the same answer. Log 1 divided by 125. Close parentheses. Don't forget to close that parentheses. Divide by log 5. Again, close that parentheses. And it gives me -3 as my answer, which is exactly the same answer I did by working it out in my head. So here is a way of solving what's called an exponential equation. I'm going to stop right here. I make sure to look on Delta Math for some examples on this, and make sure you're working on finishing up all the examples. We will be finishing the last part of this chapter on Thursday, and I will hopefully know by then exactly when your final is going to be. I will be looking forward to giving you a practice final that will be just a practice final for you. If you do very well on the practice final, I'll probably count it as, and if you did not do well on one of the other exam tests, I'll exchange the mark. Let's say you get on the practice final 90, and on one of your tests you've gotten a 70, I'll exchange the mark for you so that your average will be that much higher. Remember, you must complete everything. And look again on Delta Math for your homework. And I think this is probably going to be your last homework on Delta Math. So have a good day, and I will see you on Thursday. Any questions? You can stay around for a couple of minutes. I'll wait around for a couple of minutes if anybody wants to stay and ask me questions.